All right. So, in this chapter or in this section, we're going to talk about relative motion or the fact that motion is relative, and we are going to talk about acceleration also. In the previous video, we talked about support force, we talked about the force of friction, and we talked about speed. So, have you ever asked yourself, or do you know, or do you realize that even when you're standing, you're still moving? Think about it. You're standing, but relative to other things like the sun, you're moving. Even when you're sleeping, you're actually moving. The thing is, the earth is always moving, right? The fact that we have day and night is actually a proof that the earth is moving around the sun. When we have day, it means that the part of the earth where we are is facing the sun. And when we have night, it means that the part of the earth where we are is actually away from the sun, right? So while you're standing right now, as you're sitting, your speed relative to the sun is about 10,000 kilometers per hour, right? That sounds crazy. And that's because the earth is constantly going around the sun every 24 hours, okay? Again, think about this question. You have a hungry bee that sees a flower in a 5 meters per second breeze. How fast and in what direction should a bee fly in order to hover above the flower? Again, first of all, if the bee wants to get to the flower, it needs to fly in the direction, okay? It needs to fly in the direction of the flower, right? And it needs to have, because it needs to actually be flying at least 5 meters per second into the breeze. Okay. Now, this is another tool that Galileo used, right, to formulate the concept of acceleration. So, what he did is that he will drop a ball on a slope, and he realized that as the ball was rolling, it was rolling at increasing speed, right? Now, when he put it on an increasing slope, he realized that when he rolled a ball upward on a slope, on an increasing slope, he realized that this ball was actually rolling at a decreasing speed, right? And then when he put it on a flat surface, the speed did not change. And so he asked himself some questions, right? And so when we're talking about acceleration, acceleration is a rate of change of velocity. Do you guys remember when we're talking about quantities that have direction and magnitude? Take a pause and reflect on what name do we give to quantities that have magnitude and direction. Acceleration is one of them. Velocity is one of them. Okay? Displacement is one of them. We also have quantities that only have magnitude. Again, think about the name that we give to quantities that only have magnitude. Distance is one of them. Speed is one of them. Mass is one of them. Okay? So if you've thought about it, quantities that have direction and magnitude are called vector quantities. Okay? They are called vectors. They are called vector quantities. Whereas quantities that only have magnitude, they are called scalar right? So acceleration is a rate of change of velocity. So because velocity is a vector quantity, acceleration is also a vector quantity. So if you want to calculate acceleration, what you do is that you take the change in velocity, right, divided by the time interval. For example, if you are driving in a car with your parents, right, and on the freeway they are driving 60 miles per hour on the 215 south, what do you realize? They are driving in a specific direction, right? They have a speed of 60 miles per hour. So you have magnitude in this case and you have direction. So actually, your parents' velocity is 60 miles per hour in this 215 south direction. Okay. So velocity has two things that you need to describe it. Okay. You need to make sure you have a magnitude and you need to make sure you have a direction. So whenever you're speeding in a certain direction, actually what you have is velocity, because speed plus direction gives you velocity. I hope that makes sense. Make sure you copy this, okay? So let's check this out. You have an automobile cannot maintain a constant speed when A, when it's accelerating, B, when it's rounding a curve, both of the above. Okay. So obviously, if it is accelerating, it cannot maintain a constant speed. So A is already off because accelerating means increasing speed. Okay. When you're increasing speed, it means you're accelerating. Now, one thing you need to understand about vectors is that constant speed, by the way, means speed is not changing. Okay. So if you're driving at 60 miles per hour and you're not changing your speed, it means that's an example of constant speed. But vector quantities can sometimes their direction also influence their outcome. So if if an object is rounding around a curve, if you know how the curve is, it's like in a circle, right? It will be changing direction because if you look at a circle, if you have a circle, right? Let's say you have a circle like that. Let's say I have a circle. Up here is going to be my north, okay? And then down here is going to be my south. Here I have the east. And on this side, I have my west, okay? So rounding around a curve, you will realize that if you have a car at this position and this car is driving, okay, in that direction, what happened is that at one point, the direction of the car is going to be north, and another time is going to be east, and another time it will be south, okay? And then back to west, back to north. So because the direction is constantly changing, even if the speed is not changing, if the direction is changing, right, the car is accelerating because the direction is changing. So acceleration means two things. Either the speed is changing or the direction is changing. So you cannot have constant speed when the direction is changing. I hope that makes some sense. Okay. All right. So here we're going to be talking about. So the answer to this question, right, is both of the above. Okay. Both of the above. So the explanation is very important here. When rounding a curve, the automobile is accelerating for it is changing direction. Okay. All right. So let me go to the next slide. Let's check about this. Check this one out. Acceleration and velocity are actually A, much the same as each other, B, rates, but for different quantities. C, the same when direction is not a factor. D, the same for free fall situation. Again, guys, acceleration and velocity are not the same, okay? So I'm already thinking about B. They are not the same. But acceleration is the rate at which displacement changes with time. I mean, acceleration is the rate at which velocity changes with time, while velocity is the rate at which displacement changes with time, okay? Now let's talk about a free falling object, okay? So if you remember Galileo, when he was doing his experiment and he dropped an object on a slope, he realized that this slope was actually rolling with an increasing speed. Now, if you stand on a mountaintop and you drop an object, right? If this object is falling under the influence of gravity and with negligible air resistance, then we call this object a free falling object. Okay. So an object that falls under the influence of gravity and gravity alone is what we call a free falling object. So if you drop a pen, right, from a certain height, that pen is going to be falling, right, uh, as a free falling object if air resistance is negligible. And so what happens is that usually when you drop that object, it will start going with an increasing speed before the speed now reaches a maximum and now starts dropping at a constant speed. Now, my question to you is, if you skydive, okay, if you're doing skydiving, are you free falling? Think about it. Is skydiving an example of a free fall? All right. If a falling object gains 10 meters per second each second it falls, its acceleration is. Take note, acceleration is velocity, right? Change in velocity divided by time. So in this case, the velocity is 10 meters per second and the time is 1 second. So for you to get acceleration, you need to take 10 meters per second divided by 1 second. So that's why the answer is 10 meters per second per second. And usually the way we write it is 10 meters per second squared. Okay. All right, look at this one. You have a free falling object. It has a speed of 30 meters per second at 1 instant. Exactly 1 second later, its speed will be. So if this object gains, right, 10, 30 meters every second, then one thing is sure, right, that its speed is going to be more than 35 meters per second later, okay? Because 1 second later, its speed will be 40 meters per second, which is more than 35, okay? Look at this one. The distance fallen by a free falling body, A, remains constant each second of fall, increases each second when falling, decreases each second when falling, none of the above. The distance, okay? Take note. Distance fallen by a free falling object. As I told you, that whenever you drop an object and it's free falling, it is going to first of all start falling with an increasing speed before, right, it stabilizes at one point, okay? So if you look at this table, this is an example of a free falling object, okay? If you look at the chart here, you see time of fall is 0. So at this point, the object has not begun the journey, okay? So after 1 second that we drop that object, right, you see the velocity is 10 meters per second, okay? After the second, right, it goes to 20. The velocity is now 20. After the third second, this object is traveling at 30 meters per second. And after the fourth second, it's traveling at 40. Okay. And so if the velocity is increasing, obviously the distance covered is also going to increase because the object is now traveling at a faster speed. Okay. So when you're dropping an object and it's free falling, the velocity increases. It will increase. And even though at one point it will stabilize, but it's worth noting that a free falling object is going to fall at an increasing speed. And so if the speed is increasing, distance will also be increasing every second, or the distance it covers would also be increasing every second. All right, this brings us to the end of this chapter. I hope you've taken your note and I hope you're enjoying this chapter. If you have any questions,